Okay, physics friends, today we're going to talk about linearizing. Many of you requested a screencast of a teacher showing you more examples of how to figure out what to graph so that your slope is meaningful. Okay, so I'm just going to look at lots of different physics equations and show you how I manipulate them and then figure out what I would graph if I had that data to do so. Okay, so let's start with something simple first. So the first example that we'll look at is using an equation that we've already seen. So this is the speed of sound, or the speed of any wave traveling in a medium, is equal to the frequency times the wavelength. And let's say that I had measured speed and I knew the wavelength, and so I was interested in figuring out what the frequency was. So if I had this particular data and I wanted to graph this, I would make a graph so that this slope is equal to the frequency. Okay, and so I know that slope in math is equal to a change in y over a change in x. So this can tell me what to graph. So whatever's on the top is what I would put on my y-axis, and whatever's here would go on my x-axis. Okay, so let's take this equation and make it so that frequency is isolated, or as if it's the slope. Okay? So in order to do that, let's say I have v equals f times wavelength, so I would divide by wavelength, and I end up with the frequency is equal to v, or the speed, over the wavelength. So v is what I would put on the y-axis, and lambda, or the wavelength, I would put on the x-axis. And then the slope of my graph would be the frequency. So that's a real basic example. There are lots of others that we could do. So here's another equation that we've already seen this year, the resistance equation, or R is equal to rho L over A, where rho is the resistivity of the material, L is the length, and A is the cross-sectional area. And let's say in this lab we collected data, we knew the resistance, we had the length, and we knew the cross-sectional area, and we were interested in determining the resistivity of the metal. So I could graph it and make it so that the slope of my graph is the resistivity. And so the way that I would do that, again, is I'm going to isolate rho so that it's in the position of slope, and then whatever's on the top of my fraction would be on the y-axis, and whatever's on the bottom is what I put on my x-axis. Okay? So I'm going to isolate rho. I'm going to do that by multiplying both sides by a to get a out of the denominator. Okay. And then I get area, cross-sectional area times resistance is equal to rho times L. And then I would divide by L. And I'm left with rho is equal to area, cross-sectional area, times resistance over L. So this value I would put on my y-axis, and this value I would put on my x-axis. And then my slope would be the resistivity of the material. Okay. Some other examples. This is another one, an equation we have not yet seen. This is the period of a pendulum. So the period of a pendulum is equal to 2 pi times the square root of L over G, where L is the length of the string in the pendulum and G is the acceleration of gravity. So let's say I was on a different planet and I was interested in knowing what the acceleration of gravity on that planet was. Well, if I had the length of my pendulum, or I varied the length of my pendulum and I measured the period, I could then graph to determine what G is. Okay? And again, I want to get G in the position of slope. So how would I go about doing that? Well, I'm going to manipulate this equation by just using algebra to get G alone. So the first thing I need to do is I really need to get rid of this square root function, and by doing that, I have to square everything. So by squaring everything in here, it gets rid of the square root. And that includes stuff on both sides of the equation. So this is going to be period squared is equal to 2 squared is 4, pi squared, then L divided by G. And remember, I want G to be in the slope position, so I need to get it out of the denominator. And so to do that, I'm going to multiply both sides by G, and that gets G out of the denominator over here. And then to get it alone, I'm going to divide by period squared. So I'm left with G, or the acceleration of gravity on this particular planet, is equal to 4 pi squared times the length of the pendulum over the period squared. So this entire value I would put on my y-axis, and period squared would be on my x-axis. And then the slope would tell me the acceleration due to gravity on that particular planet. So as long as I have the right data, then I would be able to get the right answer. Okay. The next one I'm going to share with you is another different. They're kind of built one on top of each other. And again, it's equations that we have not done yet. But they have to do with circular motion as well as Newton's universal gravitational law. So when objects move in a circle, the net force is pointed towards the center, and the acceleration in a circle is equal to v squared over r. And so what we end up with is that F net, when you're moving in a circle, is equal to m times this acceleration in a circle, or AC, so v squared over r. And when, for example, this problem is going to deal with, let's say, some unknown planet of mass m, big M, and a smaller satellite that's moving in orbit of mass little m, and it's moving with speed v as it moves through at a distance, from center to center distance of r. And so I know that the only force that's acting on this satellite is the force of gravity between the planet and the satellite, or F big G, because I'm not on the surface. And that equation, that's Newton's universal law of gravitation. So F big G is equal to, you don't know this equation yet, but you will soon, big G, the little m of the satellite times the big M of the planet, all over r squared, or the distance between the two centers squared. And because my little satellite is moving in a circle, that means that Fg is the F net, because it's the only force acting on it. And so this also equals mv squared over r. So I get little m v squared over r is equal to big G, little m, big M over r squared. And the purpose of this satellite being in orbit and measuring its speed is I need to know what the mass of this planet is. Okay? I don't know. So I'm going to take the data I collect here and I'm going to graph it in such a way so that the slope of my line yields big M. Okay? And so again, I just need to get big M in the slope position, or isolated, and then what's on the top of my fraction goes on the y-axis and what's on the bottom goes on the x, based on slope. So I'm going to multiply by r squared on both sides to get r squared out of the denominator. And then over here I have r squared divided by r, so one of these r's drops out. So I'm left with r little m v squared equals big G, which is a constant, times the mass of the satellite times the mass of the planet. And again, I want to keep the mass of the planet alone, so I'm going to divide by big G and the little mass of the satellite on both sides. And looking carefully, I see that the little mass of the satellite does not matter, drops out. And so the mass of this planet, if I were to graph it to determine the slope, I would do the distance between the two times the orbital speed squared on the y-axis and Newton's gravitational constant on the x-axis, and big G is on the x-axis. And then the slope would yield the mass of the planet. That's pretty cool. I could also determine the acceleration due to gravity on that planet through a similar equation. If I was standing on the surface of this planet, then Fg, or the force of gravity, is the net force acting on me. And that would also equal big G, little m, big M, over r squared. And Fg is the mass of me times the acceleration of gravity, and that equals big G, little m, big M, over r squared. And if I want that to be my slope, I have to divide by my mass. And I end up with my mass dropping out. And so the acceleration due to gravity on this particular planet would be equal to the gravitational constant times the mass of the planet, which I got from this graph, divided by the radius of the planet squared. Okay. So these are just some other examples of how you can manipulate equations to figure out what to graph on each axis so that your slope is what you want it to be, or so that it's some meaningful quantity. Okay. In many cases, you might see a set of data given to you, for example, on a test problem or on the AP test, and then they're asking you what would you have to do to that data so that when you graph it, you get a straight line. We can do another video screencast about that later. All right? Hope this helps. Let me know if you have any questions.